Hello dear student, welcome. Today we are going to discuss measurement of insertion and attenuation loss. So for this, let us assume that there is a power which is known as an input power, and that is represented by the P1, and the power reflected at the input terminal is PR, and the P0 is represented as the output signal power, right? Before this, we know that microwave component and devices almost provide some degree of attenuation, right? And these losses are known as sometimes insertion losses, attenuation losses, reflection losses, etc. So with the help of this, we are able to measure the insertion loss and attenuation loss of a particular device or a particular transmission system. So this power actually enters the network, but due to attenuation of the network, the output power is less than the input power, right? To understand this, let us assume this is the microwave source which is generating a power Pi, right? And this is the source. This is the microwave transmission line, and this transmission line is terminated at the load impedance where we will get a power that is known as a P0, that is your output power. Here we have an power which is known as the input power, right? So when the microwave source is generating power Pi, and that power is coupled to the microwave transmission line, when the power is coupling from the microwave source to this microwave transmission line, some power is reflected back to the input side, and that particular power is known as a PR. PR means reflected power. So we can say at the input side of the microwave transmission line, the power is less than the power generated by the microwave source, right? And this power is known as a remaining power. This is your remaining power, right? And this remaining power is equal to the Pi. This is your Pi minus PR. That means what power is exactly coupled by the microwave source and the power which is reflected back by the microwave transmission line. The difference between these two powers is known as a remaining power, and that power is inputted to the microwave transmission line. Now this power is traveled from this point to the load, right? During the journey of the input of the microwave transmission line to the load end, we have a number of devices or networks, right? When the power is passed through these number of devices or networks, the power of input signal gets reduced one by one devices. So at the output we have a power received, that is your P0, and this P0 is always less than the Pi. So the difference between the Pi minus P0 is represented by the attenuation loss, which is caused by the networks or the devices, right? So the insertion loss is defined as insertion loss is defined by the difference in the power arriving at the terminating load with and without the network. That means we will consider a case when a transmission line is considered with the network, and another the case we will assume where the transmission line is considered without the network, right? So this P0 upon Pi is equal to the Pi minus PR upon Pi multiplied by the P0 upon Pi minus PR. That means in this equation we can multiply in the numerator and divide in the denominator by a value Pi minus Pr. Now taking the log of this equation, we will have 10 log P naught upon Pi is equal to the 10 log 1 minus Pr upon Pi plus 10 log P naught upon Pi minus Pr. So we can say this is nothing but your insertion loss. Insertion loss is equal to the reflection loss plus attenuation loss, right? If Pr is equal to 0, so we can say insertion loss is equal to the attenuation loss, right? This reflected power will exist in the system because the each devices doesn't perfectly match to the next impedance or next device's impedance, right? That's why there will be the some value of reflected power. To calculate the value of this one, we have two methods. One is known as a power ratio method and second is known as a RF substitution method, right? In the case of power ratio method, we consider the case as we have discussed that we consider or we set up a bench with and without the network, and we will take the reading of the power which are coming with and without the network, and by taking the ratio of these two powers we are able to directly calculate the attenuation loss. And in the second case, which is known as an RF substitution method, in this the network is replaced by an known variable attenuator. So with the help of variable attenuator or calibrated attenuator, we are able to check the reading which are or the power which are received by the network, right? Now we will see in detail. This is the bench setup for the power ratio method to calculate the attenuation loss. The bench consists of a microwave source which is used to generate the microwave signal, right? This microwave signal is generated by the gun diode and reflex klystron. In the laboratory, the output of microwave source goes to the frequency meter. Now, the frequency meter is used to measure the frequency of input signal, right? And the output of frequency meter goes to the slotted line, and the output of slotted line goes to the mass termination where the power is to be absorbed. Now, the slotted line's power is calculated by the power meter with the help of crystal detector and thermistor, right? So let us say here in this particular bench setup we have no any particular network or the devices whose attenuation to be measured. So this is your reference case. In this case, suppose we are receiving a power P1. Now we will insert a device or network whose attenuation is to be measured in between the frequency meter and slotted line, right? Like this. A device whose attenuation is to be measured is inserted between the frequency meter and slotted line. Now, by inserting these devices, we note down the power P2, which is directly recorded at the power meter with the help of crystal detector and thermistor mount. Now, we will take the ratio of P1 and P2, which is directly expressed in decibel and represents the value of attenuation, right? So we can say for this we can easily use the formula 10 log P1 divided by P2. So the value of this one represents the attenuation, but there is just some drawback, right? The drawback of this method is that attenuation measured corresponds to two power position on power meter with crystal detector. The crystal detector works on square law and hence its characteristics are non-linear. Due to this reason, the two powers P1 and P2 measured and attenuation calculated will not be accurate, and the two powers should be measured under matched condition. In unmatched condition, if it is not possible to calculate the exactly how much reduction is due to mismatch and how much is due to attenuation of the network. To remove these drawbacks, we have another device or another setup that is known as a RF substitution method. Right? The basic principle of RF substitution method is that the output power of unknown device or network is measured. The network is then replaced by a calibrated attenuator which is adjusted to get the same power. Under this condition, the attenuation of unknown device is same as indicated by the calibrated attenuator. So the circuit arrangement or bench setup for RF substitution method is this one and this one, right? In the first case, we will use a device or network whose attenuation is to be measured, and the position of this device will be in between the frequency meter and slotted line. Now, with the help of power meter, which is connected at the output of crystal detector, is calculate the power which is coming after the network. Now, this particular network is replaced by calibrated attenuator, this one, right? Now, the power by this arrangement is shown by P2. Now, we will calibrate or change or adjust the value of attenuator such that this power P2 would become equal to the power P. Now, the deflection or the value of calibrated attenuator directly measures the attenuation constant or attenuation loss of the network or the devices whose attenuation is to be measured. So this method is much simpler as compared to the previous one. So this method gives much and more accurate value of the attenuation constant. So this was the simple explanation of the how to measure the insertion loss and attenuation loss in microwave measurement. Thank you for the today.